Hi, and welcome to Module 4 of Mechanics of Materials Part 1. Today's learning outcome is to determine the maximum normal and shear stresses on inclined planes for the case of uniaxial loading. And so, uniaxial loading, the structural member is going to either be subjected to simple tension or simple compression. And so we see a graphic of that here. And I have my tensile force on the left, P. I've got an inclined plane cut with a normal and a shear force and corresponding normal and shear stresses. And so the first thing I want to do is I want you to relate the relationship or find the relationship between the transverse area and this non-transverse area, A. So the transverse area we're going to call AT. The non-transverse area is A. Okay, now that you've done that, let's do it together. I'm going to go ahead and use similar triangles. And so I've got my AT, which is the transverse area, here. And this is just the two-dimensional view. I have my non-transverse cross-section A here. I'll relate that to a similar triangle with a hypotenuse of 1. So this side becomes cosine of theta. This side becomes sine of theta. And so now by similar triangles, I have A is related to A transpose, the same as 1 is related to cosine theta. And so the relationship you should have come up with is A equals A transpose over cosine theta. And so that's the relationship. Okay, here's our structural member with the axial force P and the inclined plane revealing internal forces. We found the relationship between the cross-sectional area and the transverse area. Now we know by definition from the previous module that sigma, the normal stress, is equal to the normal force N over the cross-sectional area, or N is equal to sigma times A, or sigma, in this case, A is equal to A transverse area divided by cosine theta. And so we'll put that in up here. I want you now to do on your own the same thing for the shear stress and the relationship between the shear stress and the shear force, V. Okay, so here's the relationship. Shear stress is equal to V over A. So V is equal to the shear stress times A, or the shear stress times A transverse divided by cosine theta. And we'll put that up there. Okay, so here is my cross-section with P and N and V defined in terms of the normal stress and the shear stress. Now I'm going to apply the equations of equilibrium to relate these normal and shear stresses to my external force P. And I'll begin by summing forces perpendicular to the cut. I'll call up and to the right positive. And so I have my N force. And then by geometry, I know that this angle is theta. So I have minus P cosine theta equals 0. Or P cosine theta equals N. But we say that N is equal to sigma AT over cosine theta. And so we find that in terms of P, sigma is equal to P over AT times cosine squared theta. And let's go ahead and circle that as an important result. That relates the external force P to the normal stress. I want you to do the same thing to find the relationship between the shear stress and the shear force V on your own. Okay, coming back, now I'm going to sum forces and set it equal to equilibrium parallel to the cross-sectional face. And so I have, since I defined up and to the left positive, I have P sine of theta, which is the parallel component of this P force, minus V because it's in the opposite direction. So P sine theta is equal to V or tau A sub t over cosine theta. Or here's our relationship between tau and P. By a trig identity, I know that sine theta cosine theta is the same as 1/2 sine 2 theta. And so tau ends up being P over 2 times the transverse area times the sine of 2 theta. Here again is the relationships between the normal stress and the shear stress and our external uniaxial force P. I want to note that sigma max, the maximum value for sigma, which I'll call sigma max, occurs, well, when does it occur? At what angles does it occur? Try that on your own. And since it's a cosine function, remember a cosine function looks like this. It starts at a max, goes down like this. So this is 0 degrees, this is 90 degrees, this is 180 degrees. And so the cosine is a max at 0 degrees and 180 degrees. And so sigma max occurs at 0 degrees and 180 degrees on our cross section. And I want you to do the same thing for tau max. When does tau max occur? And if I look at a sine curve, so here's a sine curve, the maximums occur at now 90 degrees and 270 degrees. I'm looking just at the maximum value. I don't care about the sign being either positive or negative. And so at 90 degrees is the max, so theta is going to be equal to 1/2 of 90 degrees, or 45 degrees, or 1/2 of 270 degrees, or 135 degrees. And I want you to also note that the stress, the shear stress, changes sign when we go greater than 0. 0 is our theta is 90 degrees. And so here I show theta less than 90 degrees, but if I go with theta more than 90 degrees, the shear force and the shear stresses changes direction. Okay, the last thing I want to note, and this is an important result, is that sigma max, the magnitude of sigma max, what is the magnitude of sigma max equal to? Okay, so the magnitude of sigma max, that means that cosine squared theta is going to be equal to 1, is P over A sub t. That I want to relate to tau max. What's the maximum of tau? And here again, sine 2 theta being a maximum value of 1, tau max would be P over 2AT, and so sigma max is equal to 2 times the absolute value of tau max. And so that's, again, a very important result for the case of uniaxial loading. Okay, given those concepts, I now want you to do a worksheet on your own. Here's a simple model of an engineering structure. We're going to look at bar BE. It's going to be a round bar in this case, a round steel bar of 50 millimeter diameter. We're going to go ahead and neglect the weight of the individual members and wheels in our analysis. If I make that assumption, what do we call member BE then, based on my previous courses? Okay, that would be a two-force member. And so for that, we're going to do a transverse cut of that bar, find the normal stress, and do a non-transverse cut at 30 degrees and find the shear stress. And I've put the solution in the module material, and I'll see you next time.